Imagine taking your company's single most profitable product, right? Like the absolute cash cow, keeping the lights on.
Right.
And then deliberately deciding to make it 50% more expensive to manufacture. And not even by making it faster or better for your core customers.
Yeah, that's the wild part.
By welding on these highly complex, totally experimental supercomputer parts that your current customers, who are mostly gamers, don't even want. They never asked for it, and they definitely refuse to pay extra to get it.
I mean, it sounds like a textbook case of corporate self-sabotage. You implement a strategy like that, and you honestly expect to be fired by your board of directors by Friday.
Exactly. And the immediate aftermath played out pretty much exactly as you would expect. Wall Street just utterly panicked.
Oh,
The company's profit margins were obliterated, the stock cratered, and the entire market capitalization plunged to, what, a mere $1.5 billion.
yeah, $1.5 billion. They were heavily, heavily written off.
But that seemingly suicidal decision, that was the exact blueprint of how NVIDIA conquered the modern world.
It is arguably the most consequential, high-stakes, existential bet in the history of Silicon Valley.
Without a doubt.
And it worked because the CEO, Jensen Huang, understood a fundamental law of computing ecosystems that almost everyone else just completely missed. To understand the artificial intelligence revolution that we are all living through right now, you really have to understand the decade they spent wandering in the wilderness to build its foundation.
Welcome to today's deep dive. I am incredibly pumped to have you joining us today because our mission is really nothing short of decoding the mind of Jensen Huang and the engineering marvel that is NVIDIA.
It's a massive topic.
It really is. We are extracting the ultimate playbook for navigating the AI revolution. And we are doing this by looking at an extensive, just fascinating conversation from the Lex Fridman podcast featuring Jensen Huang himself.
It is such a phenomenal piece of source material. I mean, it gives us this rare, completely unfiltered look under the hood of a company that is quite literally redefining human civilization's technological capabilities.
Yeah.
We aren't just going to be talking about computer chips today. We are looking at the physical realities, the actual physics, and the first principles thinking required to build infrastructure on a planetary scale.
Okay, let's unpack this. Because usually when we talk about building a computer, there's this expectation of distinct modular simplicity.
Right, the old Lego block model.
Exactly. Think about building a standard desktop PC. You buy the central processor, you buy a couple sticks of memory, you buy a graphics card, and you just, snap them into the motherboard.
Yeah, very clean.
It's clean, it has clear boundaries, and if your computer's running slow, you just identify the bottleneck by one faster component and swap it out.
And that modular mindset has really defined consumer electronics for, 40 years? But when you step into the realm of modern AI infrastructure, that paradigm is completely broken.
Totally obsolete.
If you try to build a modern intelligence factory using that modular swap-and-play philosophy, your system will literally choke on its own data.
Why is that, though? Because for decades, we just relied on the fact that chips naturally got faster and smaller every couple of years.
Right, you're referring to Moore's law and Dennard scaling.
Yeah.
So Moore's law is that famous observation that the number of transistors on a microchip doubles roughly every 2 years, which drives down costs and increases performance.
The golden rule of tech.
Exactly. And Dennard scaling was its lesser known but equally important sibling. It basically posited that as transistors get smaller, their power density stays constant.
Okay, meaning what, practically?
Meaning you could pack twice as many transistors into the exact same space without the chip drawing more power or, bursting into flame.
Oh, wow. So you could just sit back, let the physicists do their job, and your software would naturally run twice as fast 2 years from now.
Precisely. But those laws have fundamentally slowed down. In the case of Dennard scaling, it's practically dead. You can no longer rely on physics to magically make one single chip twice as fast without it melting right through the data center floor. So if the problem you were trying to solve, like, say, training a massive large language model on the entire internet, requires 1,000,000 times more computation, you can't just build a ship 1,000,000 times faster.
You have to spread it out.
Exactly. You are forced to distribute that single problem across tens of thousands of individual computers all working simultaneously.
But the moment you split a problem into 10,000 pieces and hand it out to 10,000 computers, you run headfirst into this brutal computer science concept that Huang talks about, which is Amdahl's law.
Yes. Amdahl's law is the absolute bottleneck here.
Let's break down the actual mechanics of Amdahl's law because it really explains why NVIDIA had to completely change its business model.
Okay, so let's look at the math of Amdahl's law. It basically states that the overall speed up of any system is strictly limited by the part of the system that you cannot speed up. So imagine a task takes 10 hours. 9 hours is pure computation, and 1 hour is just moving data around through the cables.
Okay.
Even if you invent a magical, infinitely fast microchip that drops the computation time from 9 hours to 0 seconds.
The task still takes 1 hour.
Exactly.
Yeah.
Because you haven't fixed the data movement bottleneck. That 1 hour of travel time is still there.
So you could have $1 billion worth of the fastest, most advanced GPUs on Earth. But if the Ethernet cables connecting them are just standard speed, those incredibly expensive chips are just sitting there idling.
They are literally twiddling their thumbs, waiting for the data to arrive.
Wow.
And at the scale of an AI data center, that idling time costs millions of dollars in electricity and lost revenue. Distributing a workload across thousands of chips without them tripping over each other is just a massively complex puzzle.
Which is exactly why NVIDIA pivoted to a concept Huang calls extreme co-design.
Right. They realized they could no longer just design the GPU and let someone else build the networking cables or the motherboards.
They had to design the whole universe.
They are simultaneously engineering the GPU, the CPU, the high bandwidth memory, the networking cables, the switches, the power delivery systems, the liquid cooling architecture, and crucially, the software stack that runs it all.
Okay, I want to try an analogy here to capture why this is so different from traditional computing.
Let's hear it.
If old computing was like a standard vending machine, you press D4 and it dispenses a pre-made bag of chips, which is essentially just fetching a stored file from a hard drive.
Right, simple retrieval.
Yeah. But this new generative computing is completely different. It's like having a live, world-class chef trapped inside the vending machine, cooking complex meals to order in real time.
That actually captures the input-output difference perfectly.
Right.
In the old retrieval-based model, a computer was basically a filing cabinet. You request a YouTube video, the server locates the file and sends it over the internet. Very little active processing occurs.
Right.
But let's push your chef analogy further to understand the bottleneck we just talked about. The chef inside your generative AI machine isn't just cooking. They're trying to invent a completely new 50-course tasting menu on the fly. And they need thousands of specific ingredients handed to them at the exact millisecond they ask for them.
You see.
So if the sous chefs, which are the memory and networking components, take even a fraction of a second too long to hand over the salt, the entire kitchen grinds to a halt.
And to solve that, NVIDIA built a literal physical manifestation of extreme co-design. I'm talking about the NVLink 72 rack, which is part of their Grace Blackwell architecture.
It is a staggering piece of engineering.
Huang described this thing, and the physical reality of it is just wild. It is a single, monolithic metal rack containing 1.3 million components.
And it weighs thousands of pounds.
Right.
And here is where the mechanics of that rack directly solve Amdahl's law. Historically, you would ship separate servers, networking switches, and miles of fiber optic cable to a data center, right?
Yeah, and human technicians would spend months plugging it all together.
Exactly. But optical cables have latency. There's a tiny, tiny delay when you convert electrical signals to light and then back again.
Right.
For the NVLink 72, NVIDIA completely eliminated standard cables between the GPUs. Instead, they built this massive copper backplane.
A copper backplane. What does that actually look like?
Think of it as a giant, incredibly dense spine of solid copper wiring built directly into the rear of the metal rack.
Okay.
Every single one of the 72 GPUs in that rack plugs directly into that copper spine. The precision required to align those connections is so extreme, and the density is so tight that human hands simply cannot build it on site in a normal data center.
So they're essentially building a 3-ton supercomputer entirely inside the manufacturing supply chain.
Yes. They build it, seal it, test it, and ship it on a truck fully assembled.
It's not a computer in the way we've ever thought about it.
Which is exactly why Huang explicitly states that NVIDIA is no longer a chip company, they're a computing platform company. In the old days, he would walk out on stage at a keynote and proudly hold up a single silicon chip. Today, his mental model of the product he sells is a multi-gigawatt AI factory.
Which raises a really interesting question. If the factory is the product, then what is the factory actually manufacturing?
That is the core shift.
Right. Because if I buy a car factory, I get cars.
Yeah.
If a company spends $1 billion buying an AI factory, what commodity is actually dropping off the assembly line?
Tokens.
Hmm.
For the very first time in history, computation is no longer just an IT expense category on a spreadsheet.
It's a product.
The computer is now a direct manufacturer of a revenue-generating commodity, intelligence tokens.
Let's define that. A token being like a fragment of a word or a pixel or a line of code generated by the AI.
Exactly. And every token of intelligence produced by these massive factories has distinct economic value. Right now, a token generated to draft a marketing email might be worth a tiny fraction of a microscopic cent. But soon, we will see highly specialized tokens, perhaps a sequence of tokens representing a complex legal strategy or a novel pharmaceutical molecule.
Oh, wow.
Those specialized tokens might cost $1,000 per million tokens to generate, purely because of the immense economic value they provide to the buyer.
That fundamentally reshapes the global economy.
It really does.
But wait, I have to step back here. You can build the most advanced copper-spined supercomputer on Earth, but hardware is completely useless if nobody knows how to write software for it, right?
Absolutely useless.
And this highly parallel generative architecture requires a completely different style of programming than traditional software engineering. So how on earth did NVIDIA convince millions of developers across the globe to learn a totally alien, highly complex programming language?
Well, you can't just mandate that kind of global shift.
Right.
You can't put out a press release and expect 2 million engineers to just drop what they are doing and learn your new proprietary language. You have to be subversive.
Subversive.
Yeah, you have to sneak the technology into their homes, disguise it as something else, and let them discover it organically.
Which brings us back to the most dramatic corporate strategy pivot we've ever seen. That $1.5 billion existential bet we talked about at the top of the show. The CUDA origin story.
Right. To really grasp the gravity of this, we have to look at the computing landscape of the late 1990s and early 2000s.
Yeah.
NVIDIA made their name building GPUs, graphics processing units.
Yes.
These were highly specialized accelerator chips designed for one singular obsessive purpose, rendering 3D graphics for video games like Quake and Doom.
Right, because calculating how light reflects off a 3D monster requires math that is inherently parallel.
Exactly.
Like if you have a computer monitor displaying 2 million pixels, calculating the lighting for every single pixel one at a time, which is what a standard CPU does, would take forever. The game would run at like 1 frame per minute.
It would be unplayable.
So a GPU solves this by having thousands of tiny, relatively weak calculators that process all 2 million pixels simultaneously.
But Huang recognized a deeply profound tension in their business model. The better NVIDIA became at being a hyper-specialized accelerator for video game graphics, the narrower their overall market reach became.
They were pigeonholing themselves.
They were isolating themselves into a niche. He realized that to have a massive civilization-level impact on the future of computing, NVIDIA needed to evolve into a general-purpose computing company.
But that's a brutal catch-22, isn't it? Because the more general-purpose you make a chip, the heavier and slower it gets, which means it becomes worse at its core job of running video games.
It is the ultimate jack-of-all-trades, master-of-none dilemma. And to bridge that impossible gap, NVIDIA invented a software architecture called CUDA.
Let's define CA for the listener, because it's essentially the hidden operating system of the AI revolution.
CA stands for Compute Unified Device Architecture. It was basically a software layer that allowed developers to take the incredibly powerful parallel processing engine of the graphics card, and instead of using it to draw pixels, use it to solve general mathematical problems.
Okay, so a translation layer.
Exactly. A researcher could write a program in a standard, familiar language like C or C++A, run it through CUDA, and suddenly their graphics card was behaving like a supercomputer.
But this wasn't just a software patch you could download, right? And this is where the sheer audacity of the bet comes into play. To make CUDA work, NVIDIA had to physically alter the silicon of their consumer gaming chips.
We did.
They had to add new, highly complex logic circuits directly onto the silicon wafer.
Specifically, things like IE-compatible FP32 floating-point math units.
Stop right there. Break down IE-compatible FP32 for me. Why does that matter?
So FP32 stands for 32-bit floating point. It is a way for a computer to calculate extremely large or extremely precise decimal numbers.
Okay.
If you are rendering a shadow on a wall in a video game, you do not need FP32 precision. If the shadow is a millimeter off, the gamer doesn't care.
Right, they just want to shoot the alien.
Exactly. But if you are a physicist simulating fluid dynamics or a chemist predicting how a complex protein folds, you need absolute, standard-compliant, rigorous mathematical precision. Otherwise, your scientific simulation is just garbage.
So Huang looked at his core product, a consumer graphics card bought mostly by teenagers and PC hobbyists, and forced his engineers to bolt on expensive, space-consuming supercomputer math units that gamers literally would never use.
Never. They made the silicon physically larger. It consumed enormous amounts of their gross profit dollars.
Oh.
The cost to manufacture every single chip skyrocketed, but they couldn't raise the price of the graphics card because gamers wouldn't pay a premium for hidden scientific features.
That is wild. It totally explains why Wall Street punished them so severely. From a traditional quarterly earnings perspective, Huang was burning millions of dollars of shareholder value to add a feature with zero market demand.
Zero immediate demand, yes.
So what was the long game? If there was no market for it, why build it?
Because Huang was obsessively focused on a single long-term metric, the install base.
The install base.
Yes. As any historian of computing architecture will tell you, software developers do not write code for the most elegant, beautifully designed computer architecture. They write code for the architecture that has the largest number of users.
I think the battle between x86 and RISC is the perfect example of this.
It is the quintessential example. In the 1980s and 90s, brilliant engineers at companies like Sun Microsystems created RISC architectures, reduced instruction set computing.
Right.
It was elegant, efficient, and objectively beautiful engineering. On the other hand, you had Intel's x86 architecture, which powered the standard IBM PC. By all accounts, x86 was messy, convoluted, and burdened by years of legacy design.
But x86 won entirely. RISC was pushed to the margins for decades.
Because of the install base, millions of people already had an x86 PC on their desk. If you were a software developer looking to sell your program, you swallowed your engineering pride and wrote for the messy x86 system because that's where the paying customers were. Huang understood this deeply. He knew that if he built a beautiful standalone AI supercomputer chip and tried to sell it for $10,000 to universities, nobody would buy it because there was no software for it.
And nobody would write software for it because nobody owned the chip. A classic chicken and egg problem.
Precisely. So his solution was a Trojan horse. He looked at the millions of GeForce graphics cards pouring out of factories into the bedrooms and dorm rooms of gamers worldwide and decided to subsidize the AI revolution himself.
Wow.
By putting CUDA and those FP32 math units onto every single consumer GeForce card, he effectively smuggled a personal supercomputer into the hands of every university researcher, every computer science grad student, and every rogue scientist in the world.
Because all those grad students and researchers were also PC gamers, building their own gaming rigs at home.
Exactly. As Huang beautifully put it in the interview, NVIDIA is the house that GeForce built.
I love that quote.
Gamers buying cards to play Skyrim and Call of Duty inadvertently funded the deep learning revolution. When a handful of AI researchers in the early 2010s suddenly realized they could use their home gaming PCs to train neural networks millions of times faster than traditional CPUs, the spark was lit.
And because millions of people already had the hardware, an entire global community instantly sprang up around CUDA. Researchers started sharing code, writing libraries, and optimizing algorithms.
Yep.
Which really leads us to NVIDIA's true, impenetrable moat today. It's not the hardware, even though the hardware is obviously a marvel.
The hardware is replicable eventually by a determined competitor. The true moat is trust.
Trust.
When asked directly about their competitive advantage, Huang emphasized the trust of the developer ecosystem. If you are a machine learning engineer today and you are going to invest 5,000 hours of your life writing a new AI application, you target the CUDA platform first.
Because you know with absolute certainty that CUDA runs on hundreds of millions of devices, from the computer in your autonomous car to the massive cloud data centers at Amazon and Microsoft.
And crucially, you trust that NVIDIA's 43,000 employees are going to wake up every single day and obsessively update, patch, and optimize the CUDA libraries so your code runs faster without you having to change a single line.
That level of institutional trust takes a decade of suffering in the financial wilderness to build.
It really does.
And because they spent that decade building the install base, they were the only company on Earth prepared when the AI scaling laws suddenly kicked into high gear.
Yes, the scaling laws.
Let's dig into that, because scaling is like the buzzword of the decade. Everyone from Silicon Valley to Wall Street throws it around, but what are the actual mechanics of it? Where is it heading next?
So in artificial intelligence, scaling laws refer to a very specific empirical observation. Basically, as you increase the amount of computation, the volume of training data, and the sheer parameter size of the neural network, the capabilities of the AI predictably and consistently improve.
It doesn't plateau.
Exactly. It just keeps getting smarter. And Huang breaks this progression down into 4 distinct phases or laws of scaling.
Let's walk through them because it paints a really clear roadmap of the next 10 years.
Yeah.
Phase 1 is pre-training scaling.
Right. If we connect this to the models we use today, pre-training is what gave us the foundation models, things like the early GPT models or Claude.
Okay.
You take a massive corpus of human knowledge, essentially scraping the entire text of the public internet, and you feed it into the network. The AI isn't learning in a human sense. It is playing a massive statistical game of predicting the next word based on billions of patterns.
It's ingesting trillions of words to build a functional map of human language and logic.
Yeah.
But I remember vividly, just 2 or 3 years ago, a massive panic sweeping through the AI research community. Brilliant scientists were publishing papers warning that we were going to hit a brick wall.
The data wall.
Yeah. They argued that we were simply going to run out of high-quality human data to train on. The internet is vast, but it is finite.
To understand that fear, you have to look at the mechanics of pre-training. If your model gets 10 times larger, it requires exponentially more data to train effectively. Researchers calculated that we would exhaust all the useful books, articles, and websites by 2024 or 2025.
Right.
But that fear turned out to be completely misplaced, which brings us to the second law: post-training and synthetic data generation.
This is where it starts to feel like science fiction.
Yeah.
The AI is creating its own data.
Exactly. Once the models became sufficiently advanced, they crossed a threshold where they could be used to synthetically generate, augment, and refine their own training data. Think of it this way. Humans generate synthetic data for each other all the time. When a scientist runs an experiment, they write a textbook summarizing the core principles, ignoring all the messy, irrelevant noise from the lab.
They distill the knowledge.
Yes. Now, we are using advanced AI models to read messy ground truth data, distill the logic, and write highly structured, perfectly formatted textbooks specifically designed to train the next smaller generation of AI models.
That's incredible.
The data bottleneck vanished overnight. Data is no longer the limit. Raw computing power is the limit.
Which naturally accelerates us into the third law, and this is where Huang corrected a massive industry misconception: test time or inference scaling.
This was a deeply held assumption among many tech analysts.
What did they get wrong?
Well, the belief was that training a model is incredibly expensive. It requires tens of thousands of GPUs running for months. But once the model is trained, the actual act of using the model, which is called inference, would be computationally cheap.
Oh, I see.
Analysts assumed inference chips would become tiny, commoditized, and inexpensive.
But Huang completely rejects that. Why is inference suddenly demanding massive compute?
Because of how we are changing our expectations of the AI. Huang equates modern inference not to fetching an answer, but to thinking.
I want to use an analogy here. Tell me if this tracks. Let's imagine the AI as a librarian.
Okay.
Pre-training scaling was assuming the AI was just a really fast librarian. You ask a question, and it instantly sprints into the stacks, grabs a specific book, and hands you a pre-written answer. That's fast, and it doesn't take much brain power to fetch.
Right.
But test time scaling means the AI librarian isn't just fetching a book. You give it a complex problem, and it sits down at the desk. It reads 50 books, it cross-references them, it formulates a hypothesis, tests the logic against its internal models, realizes it made a mistake, backtracks, and writes a completely original 50-page thesis before it ever hands you the final answer.
That is a perfect visualization of test time scaling. Thinking is exponentially harder and requires vastly more energy than simply reading or recalling.
Right.
When you give an advanced reasoning model a complex math proof today, it doesn't just predict the next word, it engages in multi-step reasoning. It builds a decision tree, simulates different outcomes, and decomposes the problem from first principles.
Wow.
That intense thinking phase scales linearly with compute. Give the model 10 seconds to think, you get a good answer. Give a massive AI factory 10 hours of inference time to think about a cancer drug, you get a world-changing breakthrough.
And if a machine thinking for 10 hours wasn't profound enough, we are now entering the fourth law, which I think will impact you, the listener, most directly. Agentic scaling. This is the era of autonomous agents.
We need to define what an agent actually is in this context, because it's not just a chatbot with a clever prompt.
Right.
An agent is an AI system that has been granted agency. It is equipped with tools, it can access live external databases, it can manipulate software, and most importantly, it can dynamically spawn other subagents to independently complete complex, multi-step workflows.
Huang highlighted a specific open-source project called OpenClaw, which he dubbed the iPhone of tokens. He used this brilliant thought experiment about a microwave that completely reframed how I think about robotics.
Yeah, the microwave example is great.
He said, imagine a highly advanced humanoid robot in your kitchen 10 years from now. You tell it to boil water.
Yeah.
Does that robot have specialized built-in fingers that transform into microwave emitters to heat the water internally? Or does it just walk over and use the standard microwave sitting on your kitchen counter?
Naturally, it uses the microwave. It uses the tools that already exist in the environment built for humans.
Exactly.
And here is the kicker. If the robot encounters a brand new model of microwave it has never seen before, it doesn't break down, it connects to the internet, downloads the PDF manual for that specific microwave, reads it in a microsecond, and instantly becomes an expert in operating it.
And that physical metaphor translates directly to software. Software agents today are acting like that robot. If you ask an AI agent to update your company's CRM database, it doesn't need to be hard-coded with the CRM's logic. It literally reads the API documentation, writes its own custom code to interface with the human software, and executes the task.
And NVIDIA saw this shift coming years ago. If you look closely at the architecture of their newest hardware, the Vera Rubin rack, it is not merely designed to process massive text models like the previous generation.
What's different about it?
It is specifically engineered with entirely new central processors called Vera alongside massive data storage accelerators. Why? Because agentic workflows are erratic.
Erratic how?
Agents are constantly banging against databases, searching for manuals, looking up external tools, and running quick calculations. The Rubin architecture is custom-built to handle that chaotic, tool-using nature of autonomous agents.
Let's speculate deeply on what agentic scaling means for the economy, because the implications are just dizzying. Huang noted that for a CEO, it is mathematically much easier to scale a company's output by hiring 1,000 new employees than by trying to make yourself as an individual work 1,000 times harder.
And the exact same logic applies to AI. We are entering the era of multiplying AI. Instead of trying to train one massive godlike AI that can do everything perfectly, you deploy millions of smaller specialized agents working in tandem.
If spinning up a new AI agent costs a fraction of a cent and takes milliseconds, companies are going to scale by deploying massive invisible teams of digital workers.
Absolutely.
Let's walk through a hypothetical scenario because this blows my mind. Imagine a single human entrepreneur sitting in a coffee shop with a good idea. They write a detailed prompt. Instantly, the system spawns an entire temporary micro company.
Let's look at the life cycle of that micro company. Minute 1. The prompt generates a CEO agent that breaks the idea into tasks. Minute 2. A coding agent writes a fully functional web app, while a design agent generates the UI and marketing assets.
Unbelievable.
Hour 3. A deployment agent pushes the app live and secures the server. Hour 4. An advertising agent begins buying highly targeted ad space, analyzing click-through rates, and dynamically adjusting the copy.
So the app goes viral. And for a month, customer service agents handle thousands of inquiries, payment agents process the revenue, and analytics agents report back to the human.
Right.
Then when the trend inevitably dies down 6 weeks later, the human clicks a button, and the entire 50-agent company just dissolves back into the ether. No layoffs, no severance, no empty office space, just pure, on-demand corporate execution.
It represents the ultimate democratization of entrepreneurship, but as you can imagine, this explosion of autonomous agents and synthetic thinking leads to an intense, deeply personal question for you, the listener.
The existential question.
Right. If the AI is doing the thinking, writing the code, running the marketing, and creating entire companies, what is left for us humans to do? Where is our value?
That is the perfect logical transition into the human element of this technological leap. Let's talk about jobs, intelligence, and humanity. Because if you are listening to this on your morning commute, all this talk of agentic micro companies is probably inducing a fair amount of existential dread.
And rightly so. I mean, the ground is shifting underneath us. But Huang makes a vital philosophical distinction here that is almost always lost in the mainstream panic about AI taking jobs.
What is it?
He vehemently separates the tasks of a given job from the purpose of that job.
Yes, and this framework is so clarifying. He used a real-world case study from the medical field radiology. I think we really need to dive deep into this example because it proves how completely backwards our intuition can be regarding automation.
Let's wind the clock back to around 2019 or 2020. At that point, AI computer vision systems crossed a major threshold. In clinical trials, AI became superhuman at analyzing medical images, X-rays, MRIs, CT scans.
Right.
The AI could spot a microscopic tumor or a hairline fracture faster and more accurately than a human doctor with 20 years of experience.
And I remember the headlines. The immediate prediction from prominent tech leaders and economists was that the radiology profession was completely doomed. The logic seemed airtight. Why would a medical student study for a decade to learn how to look at black and white scans? And why would a hospital pay a massive salary when an AI can analyze the scan instantly for 3 cents?
The alarm bells were ringing, warning young doctors to stay far away from the field.
But look at the data today. What actually happened? Today, virtually every major radiology platform and hospital network utilizes AI vision tools. Yet the demand for human radiologists has not plummeted. It has skyrocketed. We are currently facing a severe global shortage of radiologists.
How does the economic reality contradict the seemingly obvious prediction?
It makes complete sense when you apply Huang's framework of purpose versus task. The task of a radiologist, the tedious manual labor they performed, was staring at a glowing monitor in a dark room, visually hunting for tiny anomalies in grayscale pixels. But that is not their purpose.
Exactly. The purpose of a radiologist is to diagnose disease, contextualize that diagnosis within a patient's complex medical history, collaborate with surgeons and oncologists, and ultimately help a human patient navigate a terrifying moment in their life.
Because the AI successfully took over the slow, tedious task of scanning the image, the radiologist was suddenly freed. They could review 10 times as many scans in a day.
Right.
They could catch diseases earlier, make more holistic diagnoses, and generate exponentially more value and revenue for the hospital. The hospital ended up desperately needing more radiologists, not fewer, because the core human purpose of the role was amplified by the AI.
You can take that exact same framework and apply it to coding and software engineering, which is currently undergoing the exact same panic.
Oh, definitely.
The traditional task of a software engineer was memorizing dense syntax, tracking down missing semicolons, and manually typing out thousands of lines of code. But their purpose is entirely different.
What's their purpose?
Their purpose is to solve complex business problems and design robust systems. As Huang explicitly stated, the act of coding is shifting rapidly from writing syntax to writing specifications.
It's the difference between laying bricks by hand and designing the skyscraper. If you are a carpenter and you learn to integrate AI into your workflow, you aren't just hammering nails faster. You become an architect.
Exactly.
You can use an agent to generate beautiful 3D renders for your clients on the spot, use another agent to optimize your lumber costs globally, and manage a complex supply chain. A local plumber can elevate their entire business model.
This leads to Huang's rather blunt but essential advice regarding the workforce. The person who loses their job in this revolution will not lose it to an AI. They will lose it to another human being who knows how to use AI better than they do.
Here's where I need to push back, though, and inject some realism into this. Because it gets really interesting, but also genuinely scary for a lot of people.
Sure.
It is very easy for a billionaire tech CEO sitting comfortably on a stage to dispense platitudes like just learn to use AI.
Yeah.
But let's look at this from the perspective of someone listening right now. If intelligence is truly becoming a cheap commodity, something I can buy on AWS for a few cents an hour, how does an average professional, paralyzed by the fear of obsolescence, actually pivot?
Yeah.
What does just use AI mean for someone dealing with intense daily anxiety about paying their mortgage?
That is a deeply human concern, and it's actually refreshing that Huang didn't just brush it off with a techno-optimist soundbite. He shared his deeply personal philosophy for handling immense, crushing anxiety.
Which is saying something, considering his position.
Right. Remember, he is running a multi-trillion-dollar company whose chips dictate the national security strategies of global superpowers. The pressure is unimaginable. His approach to anxiety is highly systematic and surprisingly practical.
Right, he approaches his own psychology like an engineering problem.
Yeah.
When faced with overwhelming anxiety, his first step is to aggressively decompose the problem.
Yes.
He stops and asks, what is actually happening in reality versus what is happening in my imagination? What specifically has changed in the market? What is the actual structural difficulty of this situation?
Once the problem is decomposed, he categorizes it ruthlessly. There are elements you can control and elements dictated by physics or macroeconomics that you absolutely cannot control.
Makes sense.
For the things he can control, his immediate action is communication. He stresses the absolute necessity of sharing the burden. He said, "Whatever worries me, I tell somebody else."
You don't bottle it up?
You do not sit alone in your office letting the anxiety compound. You vocalize it, and you delegate parts of the problem to the people around you who have the specific expertise to help solve it.
And then there's the final step of his philosophy, which is honestly my favorite concept from the entire interview. Systematic forgetting.
It is a beautiful parallel to how machine learning actually works.
Well, so?
In neural networks, if a model just remembers every single piece of data it ever sees, it becomes au-fitted, it becomes rigid, and fails to adapt to new information. To learn effectively, a neural network must systematically drop connections. It must forget old, irrelevant data to make room for new, generalized patterns.
Oh, wow.
Huang applies this exact mathematical concept to his own psychology.
To survive in a rapidly changing world, you have to cultivate the deliberate ability to forget your embarrassments, let go of your past failures, and drop your humiliations.
Yes.
You endure the setback, you extract the raw data, the lesson learned, and then you immediately consciously drop the emotional weight of it. You systemically forget the pain, so you can be pulled forward by the gravity of the next opportunity.
It's a profound shift in perspective. He argues that as a society, we have dangerously over-romanticized the word intelligence.
Oh, really have.
We've tied our entire cultural self-worth to how smart we are, what prestigious schools we attended, and how much specialized knowledge we've managed to memorize. But if raw intelligence is now just a commodity manufactured by an AI factory in a data center, our true superpower, our unassailable moat, lies in our humanity.
Because humanity is a vastly deeper, more complex word than intelligence. It encompasses character, compassion, generosity, determination, resilience, and a high tolerance for enduring pain.
Huang pointed out a deeply humbling reality about his own life. He noted that he is surrounded daily by 60 direct reports who are all, objectively speaking, more traditionally intelligent, more formally educated, and more deeply specialized in their respective scientific fields than he is.
Right.
Yet he is the CEO orchestrating the entire trillion-dollar enterprise, because leadership fundamentally requires those uniquely human traits that no cluster of silicon chips can currently replicate.
So the core message to you right now is this. Do not let the commoditization of intelligence paralyze you with anxiety. Let it liberate you. The core purpose of your profession remains intact. The invitation is to utilize these newly cheap tools to elevate yourself from a manual task doer into the architects of your own destiny.
But to actually achieve that democratization, to ensure that the local carpenter, the hospital radiologist, and the university student all have instantaneous access to this commoditized intelligence, requires physical infrastructure on a scale humanity has never before attempted.
It's massive.
It requires bending metal, moving oceans of data, and commanding unprecedented amounts of raw electrical energy.
Which brings us perfectly to the physical realities of engineering the future. Let's talk about supply chains, power grids, and the leadership required to build this. Because the future isn't just about elegant software algorithms floating in the cloud. It's about heavy industry.
It is heavily physical. When you look closely at the true bottlenecks of AI scaling today, they aren't algorithmic. They are intensely, stubbornly physical. We discussed the NVLink 72 rack earlier, the 3-ton monolith with 1.3 million individual components. To manufacture that single object at a massive global scale requires orchestrating hundreds of deeply specialized suppliers across multiple continents.
It requires a flawless logistical ballet, and at the center of that ballet is TSMC, the Taiwan Semiconductor Manufacturing Company. Huang spends significant time praising them, and not just for their ability to etch microscopic transistors.
TSMC's true miracle is their operational elasticity.
What does that mean?
Well, the global tech industry's demands are chaotic and shape-shifting. One month, the company needs 50,000 networking chips. The next month, they pivot and need 1 million AI accelerators. TSMC manages this violently dynamic global demand with near-perfect reliability, shifting their massive foundry resources seamlessly.
But let's say TSMC executes flawlessly. Let's say NVIDIA manages to manufacture 1 million Grace Blackwell racks. You still run headfirst into the ultimate, non-negotiable limit of physics: power.
Power is the huge one.
These AI factories require gigawatts of electricity to operate. To put that in perspective, A single gigawatt is roughly the power consumption of a mid-sized American city. Where does that electricity come from without collapsing the grid?
This is where Huang identified a fascinating structural inefficiency in how we have built our modern power grids. Currently, public power grids are engineered around worst-case scenarios.
Okay, like what?
They are scaled to handle the absolute hottest afternoon of summer when every air conditioner in the state is running at maximum, or the coldest midnight of winter. To maintain a safe margin and prevent blackouts, the grid operates at roughly 60% of its peak capacity for the vast majority of the year.
Meaning that 99% of the time there is a massive ocean of excess power generation capacity just sitting idle unused because it's waiting for a weather emergency.
Exactly. Yet, historically, data centers have operated with rigid entitlement. They demand contracts from utility companies that guarantee 100% uptime, demanding 6 nines of reliability. They install acres of diesel backup generators and put immense, unyielding strain on the grid's maximum limits, refusing to power down.
So Huang proposes a radical shift in how we think about data center architecture. Dynamic power allocation.
Yeah.
You want to build these multi-gigawatt AI factories specifically to consume that cheap, excess idle power.
Yes.
But here's the critical mechanism that makes it work.
Yeah.
The data center agrees, contractually and technically, to something called graceful degradation.
Let's unpack the mechanics of graceful degradation because it's a brilliant engineering solution to a bureaucratic problem.
Okay.
Imagine it is 2:00 p.m. in Phoenix, Arizona, in the middle of a historic July heat wave. The grid operator sees residential AC usage spiking dangerously close to maximum capacity. In the old model, the data center keeps pulling 100% power, risking a rolling blackout for the entire city.
But with graceful degradation.
The grid operator sends a signal to the AI factory. Instantly, the supercomputer begins to systematically throttle itself. It lowers the clock speed of its GPUs. It slows down the training runs.
Wow.
The latency on user queries increases slightly. Maybe an AI prompt takes 800 milliseconds to answer instead of 200 milliseconds. The factory gracefully degrades its performance to instantly release hundreds of megawatts of power back to the public grid.
That's genius.
The hospital keeps its life-saving machines running, the residents keep their air conditioning, the data center operates at a much cheaper baseline cost, and the entire system remains completely stable.
It is elegant. Yeah. But implementing that level of real-time dynamic control across hardware, software, and public utility bureaucracy requires a very specific, aggressive type of leadership.
It does.
Huang operates on a philosophy he explicitly refers to as speed-of-light leadership, and he notably despises the traditional corporate management concept of continuous improvement.
Let's contrast those two ideas because they dictate how fast a company can innovate. Continuous improvement is an iterative mindset.
Right.
If a manufacturing process currently takes 74 days, a manager practicing continuous improvement will hold meetings, tweak the workflow, and proudly announce they have shaved the time down to 72 days. It is incremental progress based on the existing baseline.
But speed-of-light thinking completely discards the baseline. It strips the problem down to the absolute, unforgiving limits of physics. It asks, if we burn this process to the ground and start it from scratch, what is the theoretical minimum time the laws of physics will allow this to take?
Yes.
And sometimes, when you run that math, the answer isn't 72 days. The answer is 6 days.
It is the difference between selectively breeding a horse over 50 generations to run slightly faster versus stepping back, studying the physics of aerodynamics and propulsion, and inventing a jet airplane.
I love that analogy.
Huang demands that his teams test every single variable memory bandwidth limits, power draw, manufacturing time against those absolute physical speed of light limits rather than against last year's performance metrics.
We actually saw this exact uncompromising philosophy demonstrated recently by a competitor. Huang highly praised Elon Musk and the XAI team for their build-out of the Colossus supercomputer in Memphis.
The Colossus build is a masterclass in this exact system-scale reasoning. Traditional data center construction of that magnitude coordinating power substations, liquid cooling for 100,000 GPUs, structural engineering takes years of planning and execution.
Years?
Musk's team achieved it in roughly 4 months.
4 months? That's insane.
Huang admired this because it required removing every single bureaucratic excuse, questioning every standard delay, and the leadership being physically present on the factory floor at the point of action.
But that raises a massive logistical question. How does one CEO, even Jensen Huang, manage an airplane factory of NVIDIA's unimaginable scale without relying on traditional tiered management structures?
Yeah, his organizational design is just as unconventional as his microchips. He currently has over 60 direct reports.
60. And here's the truly shocking part. He has 0 one-on-one meetings with any of them.
Imagine that. You have 60 high-level executives directly reporting to you, and you never sit down behind closed doors with them individually to review their work.
In a traditional Fortune 500 company, that would be considered managerial malpractice. How does anything get decided?
It gets decided through a cultural process he calls reasoning in public. When a massive problem arises, say a bottleneck in optical networking, he doesn't sequester himself in a corner office with the head of networking.
No.
He brings the problem into a forum with the entire staff simultaneously.
And the mechanism here is crucial. The expert in optical networking is in the room, but so is the expert in liquid cooling, the head of software architecture, and the lead supply chain manager. They all tackle the problem together out in the open.
It ensures total instantaneous alignment across the company. He uses these public forums and even his massive public keynotes to deliberately shape the belief system of his 43,000 employees and his global partners years in advance. He lays down the logical stepping stones day by day, explaining the why behind the physics, so that when he finally announces a seemingly radical pivot, like betting the entire company's future on deep learning, the entire ecosystem is already there. They just say, "What took you so long?"
This method of rapid, shared learning, open reasoning, and immediate dissemination of knowledge isn't just an effective corporate strategy for NVIDIA. It turns out it is the exact structural blueprint driving the most aggressive, fast-moving technological competitor on the global stage today.
Which perfectly sets up the geopolitical reality of this technology. We have to look at the global ecosystem, the rise of China, the strategy of open source, and the next physical frontier.
Yes.
Because while NVIDIA is proudly an American company, the AI revolution is undeniably a global arms race.
In the interview, Huang was remarkably candid about the rapid, formidable rise of China's AI innovation ecosystem. He didn't downplay it. He highlighted some critical structural advantages that China possesses.
They have major advantages.
First, from a pure talent perspective, roughly 50% of the world's top AI researchers are of Chinese origin. They possess an incredibly deep, rigorous talent pool in mathematics and foundational science.
Right.
Furthermore, their domestic tech industry matured during the rapid mobile and software era of the last 15 years, making their engineering workforce deeply comfortable with iterating modern software paradigms at breakneck speed.
But the cultural differences are what truly dictate their velocity. Huang described China fundamentally as a builder nation, led at the highest levels of government by engineers and scientists. He subtly contrasted this with the United States, where a significant portion of leadership consists of lawyers heavily focused on regulation, compliance, and the rule of law.
A completely different mindset.
In China, you literally have the mayors of major metropolitan cities acting like startup CEOs, fiercely competing with each other, offering massive subsidies and infrastructure to attract the best AI and electric vehicle companies to their districts.
And this intense, localized domestic competition is coupled with a highly unique cultural phenomenon regarding knowledge sharing. Huang mentioned the concept of schoolmates.
Yes, the schoolmate culture.
In the Chinese tech sector, there is a deep, abiding loyalty among university alumni. Engineers working at fiercely competing companies are often close friends or former classmates. When one engineer achieves a minor breakthrough or discovers an optimization, they don't lock it behind a corporate NDA.
They text their schoolmates.
Exactly. They share the knowledge almost instantly across company lines.
So the entire Chinese tech ecosystem functions like a massive multiplayer online role-playing game, where everyone is instantly sharing the cheat codes, the map walkthroughs, and the optimal strategies with the entire server.
I love that analogy.
No single company has to reinvent the wheel. It pushes the collective capability level of the entire nation upward incredibly fast. They are essentially open sourcing their progress by default through social networks.
Which brings us to a fascinating strategic question about NVIDIA's own behavior. Despite being a highly valuable, massively profitable proprietary hardware company, NVIDIA is heavily committed to releasing open-source AI models.
They are.
They recently released a highly advanced open-source model called Nemotron 3, and they are deep into MOE architectures.
Right.
I need to stop and ask the cynical question here. Is NVIDIA's open-source strategy just a benevolent gift to the academic community? Or is it a calculated way to ensure they own the underlying game console that everyone in the world is forced to play on? Let's talk about the mechanics of MOE mixture of experts, because it explains why they are doing this.
It is a highly calculated, brilliant strategy. Let's explain MOE, or mixture of experts.
Okay.
Instead of building one massive monolithic neural network that tries to be moderately good at everything and wastes massive amounts of compute answering simple questions, an MOE architecture contains multiple smaller, highly specialized subnetworks or experts inside of it. When you prompt the model, a routing algorithm looks at your question and sends it only to the specific expert trained for that task. A math question goes to the math expert. A coding question goes to the coding expert. It is vastly more efficient.
So to design the absolute best silicon hardware to run a MOE model, NVIDIA's engineers need to deeply understand exactly how the software layers of a MOE model are evolving. They need skin in the game.
Exactly.
They build and release these open source models so their hardware team knows exactly where the software bottlenecks will be 2 years from now.
Precisely. But the second larger reason is market expansion. While some AI models will remain highly guarded, proprietary products sold by companies like OpenAI or Google, the broader AI revolution cannot be limited to chatbots writing marketing emails.
Right, it needs to be bigger.
To justify multi-trillion-dollar valuations, AI has to diffuse into the physical world. It has to become physical AI.
Give me an example of physical AI in action.
Look at pharmaceuticals. NVIDIA is working with companies like Eli Lilly to use AI to simulate molecular interactions and discover entirely new drugs, bypassing years of manual laboratory trial and error.
That's huge.
Look at meteorology. They are using AI to predict global weather patterns and extreme climate events with higher accuracy and a fraction of the compute of traditional supercomputer weather models. Look at automotive companies using AI to simulate complex aerodynamic fluid dynamics to design more efficient cars.
If all AI models were strictly locked behind expensive, proprietary APIs, university researchers and legacy industries like agriculture or heavy manufacturing couldn't afford to experiment freely.
They'd be shut out.
By open sourcing incredibly powerful models like Nemotron, NVIDIA essentially hands out free toolkits. They ensure that every single industry on the planet plugs into their ecosystem, guaranteeing that CEO remains the inescapable universal foundation of global computation.
So the inevitable question becomes, where does this universal foundation go next? When you extrapolate these scaling laws to their logical extreme, you quickly circle back to the physical bottlenecks we discussed on Earth.
Right.
Power grids are constrained. Liquid cooling requires massive amounts of fresh water. Land for gigawatt data centers is becoming scarce. And suddenly, an environment that sounds like pure science fiction becomes a highly viable logical location for a data center. Space.
It sounds insane until you look at the mechanics of what is already happening.
Yeah.
NVIDIA GPUs are, at this exact moment, orbiting the Earth, operating on satellites.
Exactly. And they are there to solve a very specific bandwidth bottleneck. Right now, there are constellations of advanced satellites with incredibly high-resolution cameras capturing centimeter-scale imaging of the Earth's surface continuously.
Okay.
The sheer volume of raw data they capture, petabytes of telemetry, imagery, and sensor data, is far too massive to efficiently beam back down to Earth using radio waves. The latency and bandwidth constraints make real-time analysis impossible.
So instead of trying to force a fire hose of data through a tiny straw, you bypass the bandwidth bottleneck entirely. You put the AI inference engine at the absolute edge on the satellite itself.
Exactly.
The GPU processes the imagery in real time in orbit. It looks at the data, throws away 99% of the useless images, like thousands of pictures of empty oceans or cloud cover, and only beams down the critical actionable insight. Here is a ship moving in a restricted zone. Here's a wildfire sparking.
Of course, computing in the vacuum of space introduces its own extreme physical challenges. On the plus side, you have access to 247 uninterrupted solar power if positioned correctly.
Right.
But cooling is a nightmare. There is no air in space to power convection cooling fans. You have to rely entirely on thermal radiation to bleed the heat away from the chips. Furthermore, you have to physically harden the silicon against relentless bombardment from cosmic radiation that would instantly fry a standard consumer GPU.
But as Huang casually noted, space is incredibly big. We can build giant thermal radiators. It is the ultimate manifestation of his philosophy of extreme co-design. It is taking the speed of light limits and literally pushing them into orbit.
Which brings us to the end of this journey, and it's time to bring this massive, sprawling deep dive full circle for you. We started our conversation today by looking at a standard desktop PC, a simple, comforting, modular box with discrete components that we could easily understand.
And we've journeyed incredibly far beyond the boundaries of that box. We've explored the absolute physical necessity of extreme hardware co-design at the massive multi-ton rack scale. We uncovered the billion-dollar existential gamble of bolting supercomputer math units onto video game chips and how that Trojan horse created the CUDA moat.
We've traced the evolution of the scaling laws, moving from models that simply memorize the internet to a new reality of autonomous agents that synthesize their own data, think critically, and can spawn temporary, fully functional microcompanies in seconds.
And perhaps most importantly, we arrived at the profound realization that in an age where raw intelligence is manufactured in gigawatt factories and sold as a cheap commodity, your humanity, your resilience, your empathy, your leadership is your greatest unassailable asset.
The invitation here is clear and hopefully empowering. The core purpose of your job, your role in society, remains completely intact, even as the specific manual tasks you perform daily are automated away.
The challenge is to not let the sheer scale of this automation paralyze you with anxiety, but to consciously choose to become the architect of your own profession by wielding these incredibly powerful new tools.
So as we wrap up, we want to leave you with one final, genuinely mind-bending concept from Jensen Huang to mull over on your own time.
Oh, this one is a trip.
When asked to speculate about the distant future of this technology, he casually laid out a vision for the reality of interstellar space travel. He envisions a scenario where humanity sends a highly advanced, AI-powered humanoid robot on a spaceship out into the deep cosmos, traveling for decades.
And while that physical robot is hurtling through the dark vacuum of space, back here on Earth, your entire human life is being meticulously recorded. Your inbox, your daily conversations, your ethical choices, your memories, your specific patterns of reasoning, all of it is perfectly captured, learned, and digitized into an incredibly dense AI model of your consciousness.
Then years later, once your digital consciousness is perfectly formed and trained, humanity beams that data via laser at the speed of light to catch up with the robot light years away. The robot receives the transmission, downloads your digitized mind, and wakes up on an alien world, exploring the stars as you.
So we ask you to consider this. If your intelligence, your reasoning, your memories, and your personality could be cleanly separated from your biology, beamed as pure data to a humanoid chassis light years away, where does your humanity actually reside?
It is a profound question that completely redefines what it means to be alive and what it means to be human in the digital age.
We started this hour looking for the comforting, binary precision of a microchip. But as we step fully into this new generative era, we realize the boundaries between hardware, software, and human thought aren't just murky, they are entirely limitless. Thank you so much for taking this extensive deep dive with us today. Keep questioning, keep learning, and we'll see you out there on the frontier.